Okay, well, let's thank Mark again. Thank you for your talk. And I'll introduce the fifth talk of this session will be titled Current and Future Opportunities for Non-Ambient Condition Earth Science Experiments at the ALS. Will be presented by Martin Kunz from the Advanced Light Source at Lawrence Berkeley National Laboratory. Okay, please take it away, Martin.
Thanks for the organizers to giving me the chance to uh, present some aspects of ALS, Earth Science activities. I am the ALS staff scientist being responsible for the high pressure beamline 1222, which we operate in collaboration with Compress. That beamline has been extensively covered in the talk this morning by Quentin Williams, so I will take the liberty to actually veer a little bit away from high pressure geoscience, and I will use my talk to shed some light on general earth science opportunities at ALS and the effect of ALSU or the influence of the ALSU on those experiments. On this background, this is my outline. I will give some condensed version for the ALS of what Mark just gave. It helps a lot of some of the background he gave, and I will then focus on the most important programs at the ALS where earth science is being performed, some of them at non-ambient conditions, some of them also on quenched or retrieved samples. 1232 and 832 are like 1222 hard X-ray beamlines. The ALS has a fairly successful infrared program, which was also supporting Compress during the NSLS2 transition. And then the actual focus of ALS beamlines, straight section beamlines, are the soft and tender X-ray beamlines. And I will comment on the Earth Science program and on some of those beamlines and what the ALSU does to them as well. So let me first go a little bit on what the ALS is and what the ALSU will does to it. The ALS is compared to the APS and the ESRF and also Petra, a relatively small 200 meter circumference synchrotron storage ring. It's housed in a historic building of Florence's former 184-inch cyclotron on top of the East Bay Hills, overlooking the beautiful San Francisco Bay, provided there's no smog or no smoke. And the ALS got first light a little more than 30 years ago. It operates at 1.9 GeV. That's a much lower energy than the other synchrotrons we have heard today. It has a 500 milliamps top-off current in the storage ring. And this energy, together with a relatively small circumference, leads to maximum energies in the straight sections, 12 of which we have, which peak in the soft to tender X-ray range. The ALS underwent numerous upgrades in its 30 years history, and one of them actually, based on strong user demand, introduced superbands, 3 superbands at their bands, and those superbands between 4 and 5 Tesla field strength have a critical energy around 12 keV, which push the useful flux and brightness into the hard X-ray range up to about 20. Some beamlines even use up to 60 keV photons. These numerous upgrades also compressed the beam to the current size, and this is sigma sizes of about 250 microns by 8 microns. So it's much wider and than it is high, which is the same as you've seen for the APS before. Now the LSU will do. These pictures all look a little bit the same as APS, ESRF, Petra, and the others do. It will go as a upgrade to what they call the ultimate storage ring. And this is being done in a similar way. The current 3-band multiband achromats are being replaced. In our case, they're actually replaced by 9-band multiband achromat. An additional feature of the ALS, which I don't think the APS nor the ESRF have, is that in order to guarantee continuous smooth top-off operation, we actually install a complete separate storage ring on the inside of the current storage ring. And this is shown on this graph. And this storage ring, this additional storage ring named accumulator ring, will be used to dampen the oscillations in the electron bunches, and thus enable what they call swap out injection on the run. at 500 milliamps. The new storage ring will operate at 2 giga-electron volt. That means we're actually going a little up, not down as the APS, and we continue at 500 milliamps. The increase from MBA 3 to MBA 9 the main effect of, and the decrease in source size, the main effect of these upgrades is that the flux and brightness in the soft to tender X-ray energy range will go up to the highest of any synchrotron worldwide. On the contrast, the higher energy range will go down a little bit. This will be partially compensated by replacing the current superbands by 3 Tesla warm bending magnets. And as Mark just showed, this will increase the brightness in the low tens of keV, but the crossover with compared to the current superband will be around 30 keV. Timeline is it will kind of piggyback behind the APS shutdown, and I think that's by design. Current plan is the start of the shutdown is April 25, and the end of the shutdown is supposed to be summer 26. Now let me go and shed some light on what this upgrade does to the current Earth science programs at ELS and what the current Earth programs at ELS will be. I will say some short words on what's happening at 1222. Quentin covered most of it. 1222 is one of the beamlines that benefits from the superband program. It has an energy range between 6 and about 35 keV. One thing which is really appreciated by our users that we can easily tune the energy. We let users change their energy, which is, for example, being used by people who do radial diffraction when they need to find their sample in a gasket that has low absorption contrast to their sample. But besides a strong demand from the diamond anisel community, we also have a strong demand from the general community who seeks to do X-ray diffraction under non-ambient conditions with any kind of ancillary equipment. And in particular, a particular example, successful example was the catalyst community, which approached us with the need to do in situ X-ray diffraction under controlled atmosphere and high temperature. Together with them, we developed this lamp heater, which is now used across the field, and it's very, very successful and can definitely also be used for earth science applications, for example, carbon mineralization. And especially if, as we plan, add a quantitative vapor phase, or we revive a sapphire cell, which allows us to go to CO2 supercritical conditions. The impact of the LSU upgrade on the operation of the beamline 1222 is that it will reduce somewhat the intensity, but all the diamond anisel work is brightness limited because we refocus the source onto the small sample volume, and we gain brightness about a factor of 1.6. Not exactly the orders of magnitudes, but plenty to satisfy a lot of demand, which does not necessarily need the absolute highest brightness. Next, I want to talk about the ALS's Low X-ray microrefraction program, which is operated by Nobumichi Tamura on beamline 1232. 1232 draws its X-rays from the same superband as 1222. It has slightly different primary optics. It has a white beam with energy range from 5 to 25 keV. This white beam is focused by a kb arrangement onto a submicron beam into a sample that is in reflecting geometry with the detector at very high angle. And at each spot of the sample, which can be scanned very fast underneath the beam, a sub-second exposure is produced, and this allows Nobumichi to create maps of lower diffraction patterns in a millimeter range with 1 micron resolution. The data that can be gained out of a lower diffraction pattern is that you can get grain orientation maps, crystalline phase maps, deviatoric strain maps, and also maps with information on plastic deformation. The obvious condition to have this experiment be successful is that the grain size needs to be at the order of magnitude or bigger of the X-ray size. That means around 1 micron. If this condition is not or partially fulfilled, the beamline has the opportunity to rotate in a 4 crystal silicon 111 monochromator advantage of this 4-crystal monochromator is that it leaves the beam position at the exact same spot where the white beam was before it did this. And it can then move and combine polychromatic white beam lower diffraction with monochromatic, traditional monochromatic reflection powder diffraction experiments. In earth science applications, the most common kind of samples are petrographic thin sections where scans with maps are produced with this kind of information I mentioned before, that is phase maps, rotation maps, strain maps, etc. That doesn't mean that beamline cannot be interfaced with some kind of non-ambient conditions, mostly temperature, temperature stage. They can do mechanical stresses and pressure, and there were also actually published examples of diamond anvil cell work on combining with lower microrefraction on beamline 1222. This was by Shaoling Xu, who was first a doctoral fellow at ELS and then a postdoctoral fellow together with Lowell Miyabi. Microrefraction is an inherently brightness limited experiment, and at the source point of the 1232, the ALSU would increase the brightness by a factor of 2.7. So this program would definitely benefit from the ALSU upgrade and would certainly continue to be very successful. A few science examples, a couple of science examples, what's being done in earth science at 1232. I'll start here on the right side. This is a series of publications which came from a program which was initiated actually by Rudi Wenck, who recognized again, as they did in other instances, that methods being commonly used in material science could well be applied to geoscience. In this case, he realized if he applies the stress and strain mapping on quartz crystals in petrographic slices, you can actually retrieve residual stress and strain in the rocks. But this basically used these quartz crystals as paleopiezometer in the rock. And a very neat example he did, he actually had a sample from the type locality of the boudinage, the common structural feature in the rocks, which when I was a student were interpreted as an extensional stretch feature, but now is regarded as being actually due to compression. And Rudi and his co-workers showed that actually, indeed, the stress field in these quartz lenses in the boudinage was compression, not extension, using the lower microrefraction mapping technique. Another example which shows how useful this technique can be to mineralogists is the fact that if you're working with crystals or minerals which are unique and cannot be prepared out of your sample, you're relying on non-destructive techniques such as allowing microrefraction to extract structural information, which is needed to get it accepted by the International Mineralogical Association as a new mineral. This collaboration between Russian and Canadian scientists found their continuous use of beamline 1232 so helpful that they decided to name one of their new minerals they discovered after the beamline scientist Nobumichi Tamura. So there's now a Tamuraite out there in the world. And if I'm not mistaken, that's probably the only beamline scientist who has a mineral named after him. Next, I want to spend some words on the ALS's microtomography program, which runs on beamline 832. Another superband source. Here, there's absolutely no optics between the source and, with some restriction, no optics between the source and the sample. It can be operated in wide beam, and the beam size at the sample is about 4 centimeters by 5 millimeters. When I say no optics, I neglected that they have the option to put two types of multi-layer monochromators with various bandpaths into the beam path. And depending on their application, they use this pink beam or the white beam mode. They have a fairly state-of-the-art camera system, which very fast readout, which allows them actually to go to very high scan rates, such that the full scan temporal resolution can be as short as 2 seconds. Their spatial resolution depends on the field of view they choose, and the smallest field of view, which is a little less than a millimeter, they have 0.35 micron pixel size. And their largest field of view, the resolution decreases to 9 micron pixel size. What makes this beamline especially attractive, I think, also for earth science applications, and in general, with what it uses to compensate for the lack of flux compared to other tomography beamlines, is their extreme versatility in terms of non-ambient conditions. They have non-ambient conditions sample environments which cover almost all combinations from mechanical stress, pressure, and temperatures. And they even have what I dubbed an online garden, which allows them to do in situ plant physiology experiments. Another thing which is very well advanced and developed at ALS tomography beamline is that it was actually the birthplace of the ALS's program to streamline data analysis, on-the-fly data analysis, and data pipeline. The impact of the LSU is that the flux will be reduced, but it will still be in a very useful range, and I'm sure the program can be continued successfully, not at least thanks to their very advanced non-ambient condition environments. Just two quick examples on science that can be done. Michael Manga has an ongoing successful program where he uses tomography to elucidate the physics of lava eruptions in volcano. This particular example, he looked at the pore space in pyroclasts from a recent Hawaii eruption and could, with the help of the tomographic experiments, formulate a model how this multi-scale fragmentation of these pyroclasts happens. Another community, earth science community, that uses the ALS tomography a lot is the petroleum extraction community. And in this particular case, they investigated the stress reaction of high pressure fluid induced fractures in shales and how this affects the flow through these fractures. Let me then say some things about the ALS infrared program. The ALS has 3 beamlines that do infrared microspectroscopy and nanospectroscopy. Beamline 1.4 and 2.4 do traditional microspectroscopy, where the beam, the spatial resolution is limited by the diffraction limit. They have a big spectral range, and given the large working distance, they allow for a variety of sample measurements. That's also the beamline 1.4, where the compressed infrared program was housed during the NSLS upgrade. They still can do diamond anvil cells experiment, provided that the diamond anvil cell has a fairly small cross section. But they also have microfluidic cells and cryo-cooled opportunities. Beamline 5.4 is one of the birthplace of synchrotron infrared nanospectroscopy. This is a trick, a very ingenious trick to bypass the diffraction limit, in that the infrared beam is interfaced with an AFM tip. The scattering of the infrared beam off the AFM tip creates a feedback with the sample, and it's this off-scattered infrared beam that is analyzed with a FTIR spectrometer. With this, the spatial resolution gets limited to the size of the tip to below 25 nanometers. Obviously, this technique is not so convenient to be interfaced with non-ambient condition samples, but it can still well be used for retrieved or quenched samples. And this is also shown in the productivity, the earth science productivity of the infrared program at the ALS. A large part actually is in collaboration with Andrew Westphal on the Stardust spacecraft program, where they analyze many of the samples that have been retrieved from the Stardust spacecraft and produced a range of really high-profile publications. Apart from Stardust, there's a lot of infrared experiments at the ALS going on in conjunction with diffraction experiments, either at the ALS or the APS. For example, here the IS7 inclusion, which Vitali reported on this morning, or Dan Shim, who works on water solubility in dense silicates, also either in conjunction with ALS diffraction or APS diffraction, or then experiments on clays under non-ambient condition, or more general on chemical heterogeneity in shale rocks. Finally, some words on kind of the strength of the ALS, namely the soft X-ray spectroscopy and imaging programs. There's various Dixon beamlines and the Tender beamline at the ALS. and a tender to hard X-ray spectroscopy beamline at DLS. These beamlines all operate in the soft to tender energy range. Current beamline 1032 operates on a warm band and goes up to 17 keV, and thus provides spectroscopy up to first order transition metals, first order transition metals, and also phosphorus, sulfur, and chlorine. These Dixons and Cosmic run more in the lower energy range and provide a two-dimensional or three-dimensional through tachography imaging experiments on geologically relevant samples. Their ALSU impact will be positive. 1032 actually will move to the newly LSU beamline, tender beamline, which has two branch lines, a scattering beam branch line, which reaches from 1 to 5 kV, and a nanoprobe, which reaches from 2 to 8 kV, which will be mostly interesting probably for earth science applications. The spatial resolution for tachography experiments will be 10 nanometers, and for X-ray absorption experiments will be in 100 nanometer range. Cosmic will be also upgraded in the LSU project and will gain a 10-time increase in coherent flux on the sample. As you can imagine, the non-ambient condition opportunities for these kind of beamlines is a little restricted on one hand because of their low energy range, on the other hand because of the very short working distances. However, in the example of 1032, that can actually still be combined with cryo opportunities, and also what is actually really nice, it's in a beamline where you can easily combine X-ray absorption spectroscopy and powder diffraction, and therefore can provide multimodal analysis. Just a couple examples of earth science. That's perfect timing. Earth science experiments at soft and tender X-ray beamlines at ALS. Here on the right side is an example from Brandy Toner, who does a lot of experiments or research in deep ocean. In this particular example, she was looking at the biotic versus anbiotic genesis of iron oxide precipitation at hydrothermal vents in the deep ocean. And she uses sticks as one of the tools for her experiments in order to actually correlate the iron content with the actual particles. And she finds that it's mostly in these microbial mats surrounding these hydrothermal vents in the deep ocean. This experiment is a nice experiment from paleontology, where infrared is combined with spectroscopy on 1032, and they actually managed to demonstrate that soft tissue from this Tyrannosaurus rex in the Smithsonian is indeed orthogenic, and they managed, with the data from the infrared and the X-ray spectroscopy, to propose a model which is based on non-enzymatic protein cross-linking, which they also could actually then prove by the fact that they reproduce it in modern chicken blood vessels, which then gave them very similar data as the ones they retrieved from the fossil dinosaurs. And with this, I want to thank you again for the opportunity to talk here, and of course, thank you to various sponsors and supporting institutions.
Thank you, Martin, for your very interesting talk. It's very exciting to know that there's so many beamlines at ALS that do high pressure work.